Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants, and today we are looking at hybridization. Specifically, we're going to be determining the hybridization state of the central atom in the following molecules. And then later on, we'll get into a little bit more detail about how to represent those hybridized states. So let's start with the first one. It's boron trifluoride, which if you were to draw it, it would look like that. Make sure you use all your electrons when you're drawing these out. It is very important. Okay, and as you can see from this picture, this uses all the electrons involved. We are dealing with an AB3 molecule. It is essential to learn these generic terms. Some places may call it AX3, but we're going to use AB3. And because it's AB3, we know two things. We know its geometry, and we know its hybridization for the central atom. Because when we're talking about in terms of AB3 or AX3, we're talking in terms of the central molecule, central atom of the molecule. So we know from our geometry that this is trigonal planar. And we also know, and again, just like with the molecular geometry, this is going to be a chart in your book that you're going to want to memorize in terms of which generic terms yield which hybridized states. And in this case, AB3 yields an sp2 hybridized state for the central atom specifically. The fluorines are still going to follow the same rules, but the central atom, the same rules in terms of their orbitals. It is the central atom that's going to slightly skew because of the pull that the surrounding atoms have on the central atom's electron cloud. So let's look at beryllium chloride. Beryllium chloride is linear. It's just and in fact, it's not really a molecule. We're dealing with an ionic compound. But for the sake of argument, let's work through all this. Beryllium chloride is going to give us a linear molecule because it is AB2. Again, beryllium is probably one of the ones that would not make as much sense in this case, except to say that what really is happening is that this is an ionic compound. But for the sake of practice, we'll just go ahead and call it a molecule and say it's AB2 and linear. And so it would have the sp hybridized state. A really big example of sp hybridized states would be as if you have a carbon triple bonded with a carbon. That's sp hybridized. That's always going to be sp hybridized. Okay. Last one on our list here is phosphorus tetrabromide, which is going to have a phosphorus and bromines here, 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 and finally there. And each of the bromines have their electrons, their lone pairs. Okay. So this would definitely be an AB5. And this would be, according to your geometry, it would be trigonal bipyramidal. and it would be sp3d for its hybridization state. And again, that is something that you're going to have to look at and memorize from a chart. You're going to memorize it based on your generic formulas. You're not going to worry about that, oh, phosphorus tetrabromide is always going to be sp3 for the central atom. Well, that's true, but there are millions and billions of combinations that you'd have to recall if that were the case. Just memorize it in terms of the generic formula, draw the molecule out, and from that from that molecule picture, you can write the generic formula, and from there you can get your geometry and your hybridized state. Okay. So, getting into a little bit more detail, let's look at a description of the hybridization state of sulfur in sulfur hexafluoride. So for sulfur hexafluoride, sulfur has 6 valence electrons, fluorine has 7. So we've got 1, 2, 3, 4, 5, 6. And recall that sulfur is in period 3, so it can have the expanded octet, which is what you're seeing here. Because the first thing when you see this many bonds to a single atom should be, can it have an expanded octet? Because if it can't, then you just need to reconfigure the molecule so that it fits properly. But you have to use all the electrons, and if it needs that expanded octet and it is allowed to have it, that's fine. If it can't have the expanded octet, then you have to re-evaluate it. And from looking at this molecule, you can note it's an AB6. There are 6 atoms attached to the central atom. And so it is octahedral. And that's giving our geometry of it. But let's look at how we can represent this hybridization state. From the sp6, you can find that the hybridization edit. From the AB6, you can find that the hybridization should be sp3d2. And to better describe that, let's look at our electron configuration. If you recall, when you were working on the Hund rule, you would have a box for S and 3 boxes for P, 1 for each direction in space. So for the Hund rule, if we were looking at sulfur, which has 6 valence electrons, we would fill it up like so. And that would be true if it was by itself. But because we're looking at the hybridized state, sp3d2, we're going to create a different makeup of where those electrons should go and how they should look. So let's take a look. They're going, for sp3d2, there are going to be 6 boxes. Now you're wondering how I knew there were 6 boxes. And the reason is, if we were to pretend like there was a 1 there for the S, then there would, if you count them up, if you add every exponent together, you would find that it equals 6. 1 plus 3 is 4, plus 2 is 6. Okay? From here, we can fill in our electrons. And you'll note that they're all going to be going up. None of them are paired off. So that's our sp3d2 hybridized state for sulfur in sulfur hexafluoride. Let's look at the bonding of something a little trickier for dichloroethylene. Now, this is something that occurs more in organic chemistry, but it's good to get used to the nomenclature now. So this is a rather generic term, but it can form in many different conformations or several different conformations. But we're just going to focus on one today. I'm going to choose it at random. So this double bond has to do with the ene at the end, and the fact that there's two carbons has to do with the ethyl component of the name. So the ethylene means that there's two carbons that are double bonded together, and then the dichloro means that there's two chlorines. So that means if carbon makes 4 bonds, then there's a bond, there's a spare bond for each carbon, which will be taken up by hydrogen. So let's do it like this. Let's just put hydrogen down here and hydrogen down here, chlorine and chlorine, and we're just going to put our lone pairs over here. Okay, so that's dichloroethylene. That's one of the conformations of dichloroethylene. But regardless of the conformation of the molecule, it's always going to have the same, it's going to have the same molecular geometry, more or less. Okay? And so if we look at a given carbon, let's look at this carbon. Okay? If we look at a given carbon, we're just going to look at the geometry of that specific carbon. So we have a carbon with no additional lone pairs on it that's bonded to 3 other species, 3 other atoms. So that tells us that it's going to be trigonal planar. We're going to treat this as 2 separate molecules almost. And in fact, the carbon on the left will have the same makeup in terms of the overall molecule. What you have to do when you're looking at larger molecules is split them into groups in order to determine their overall geometry, because eventually you get into molecules that are so large it's almost nonsensical to attribute a simple geometry to them. So we take it into groups, and we're taking carbon as our main group because it's attached directly to the other species. Okay. So we've got trigonal planar is on either side. Either side is making a trigonal planar shape. And we can look at the hybridization of any given species in this molecule. Now, for hydrogen, that's really simple. Hydrogen doesn't really hybridize. It's got that 1s, and it's going up. That's it. That's hydrogen. Done. Chlorine has 1 bond to carbon and 3 lone pairs. So when you look at that, it's almost as though it's attached to 4 different species. 4 things are attached to it. You would treat this instance similar to as if you had a carbon attached to 4 hydrogens. So for chlorine, the norm, at least at the latter stage, we would have the 1s, 2, 2s2, 2p6. But let's just look at the third period for the sake of brevity. So we got 3s, they go up and down, and there's 7 total valence electrons. We're only looking at the valence shell here. So 3p, and 1, 2, 3, 4, 5. 5 plus 2 is 7, so that would be what you would normally see for chlorine. However, because of its hybridized state, it has those extra electrons. We're going to kind of treat it like an sp3. So that sp3 is going to have 4 boxes. And in those 4 boxes, we're going to put 7 electrons. So 1, 2, 3, 4. And interestingly enough, in hybridized states, instead of putting the paired electrons starting from the left and working right, it appears as though it starts from the right and works left. So we're going to do 5, 6, and 7. And that's how sp3 for chlorine would look. The last one, and probably the most relevant one, is carbon. Now, normally you would look at carbon and say, okay, in its valence shell, again, we're only dealing with the valence right now, you'd have 2s up and down. Let's shorten that up. You have 1, 2, 3, 2p, and you'd have like that. That would be the normal carbon. However, carbon attached to 3 other components with no lone pairs to change the shape slightly would be an sp2. AB3 yields sp2 hybridized. So we've got 1, 2, 3, and it's sp2. Okay, so filling in the electrons, we've got 1, 2, 3, and 4. So that's the basis for hybridization. Obviously, there's a lot more to it that you'll have to learn in your class. But when addressing hybridized states and trying to describe them in their most simple terms, this should be sufficient.